Hi, I'm Drew James, and welcome to the Canada, Spokane, and Pacific Railroad. At last year's NERX, I had the opportunity to give you a tour of the layout, and today I'd like to show you the new CTC machine that we built for the layout. As I described last year, the CS&P was built for operations. And part of my desire as we were designing and building the CS&P was to have a CTC machine. I didn't know much about them, but in 2018, I did have the opportunity to go to the Kansas City National Convention. And at the convention, there was two things that really had an impact on me. The first was, in one of the layout tours, I was able to see the spectacular O-scale C&O layout of Jim Udaley's, who has a large operating CTC machine. And the second thing was I sat through two outstanding clinics by Paul Geiger, where he described how a CTC machine works and how he built his. Those actually, his outstanding clinics are still available on the NMRA website. So today I want to do three things. The first is to provide just a short overview of what is centralized traffic control and how does it work. The second thing is I'm going to walk you through the machine and how it works, how you operate a CTC machine, at least the basics of it. And then the third thing is I'll provide a quick description of how we actually built and constructed this machine. Let's first quickly talk about the various traffic control methods that are used by the railroads and also are found on model railroads. The first type is timetable and train order. This was used in the classic era. And in timetable and train order, train movement is authorized by the employee timetable and can be modified and augmented through dispatcher's train orders. And the train orders are transmitted to the crews via station agents. So a dispatcher would call up or use a telegraph to provide an order to a station agent, who then could hoop it up to the train crews or set a signal so that the train crew would know to stop to pick up their orders. The next mechanism is track warrant. Track warrant is taking advantage of the new technology of when radios became common on the trains. And with radio communication, now the dispatcher no longer has to go through a station agent to issue a train order, but can issue authorized train movement directly to the crew via warrant over a radio. The next common mechanism is CATS. CATS is the most modern traffic control method, computer automated traffic system. And with CATS, this is where the railroads will have generally a large centralized dispatching center. They'll use computers to keep track of where all the trains are, to monitor their safe movement, and the dispatchers can throw turnouts and route traffic through a touch of a mouse. We're obviously going to be focused on CTC in this presentation, but before I get to CTC, I want to just touch on how ABS, automated block signaling, fits into CTC. So when you hear automated block signaling, think of this as being primarily a safety feature. It's not for traffic control, but it's really for safety of the trains. I often think of it as ABS as being an automated flagman protecting the train. So when you hear CTC, CTC incorporates all of ABS, all the ABS safety features, but in addition, it adds the function to actually authorize train movement. ABS alone does not authorize train movement. It simply is saying whether it's safe to proceed or not, but not whether the dispatcher has authorized a train to proceed. Centralized traffic control systems came about in the 1930s is when the earliest systems were installed. They were common up until the 1980s. I modeled 1981 and they were still in fairly common usage then. When you get into the 1990s, they started to be replaced by more computerized systems. There are two primary companies that provided CTC systems. Union Switch and Signal was definitely the largest. They were located in Pittsburgh. They provided the majority of systems. General Railway Signal was also a large supplier. They were located in Rochester. Now, Union Switch and Signal, besides providing the majority of machines, their machines also tended to be standardized. So that's a picture of a US&S machine on the slide. And most of the machines, their machines look very similar with standardized usage, standardized panels, etc. Well, GRS were very custom. And so I think that every CTC machine I've seen on a model railroad or in a railroad museum has been a US&S machine. I don't think I've ever actually seen a GRS machine in person, although I've seen pictures of them. In CTC, as we discussed previously, the train movement is authorized by the block signals, and the dispatcher can control the key signals. Now, the dispatcher doesn't control every signal on the railroad. So when you have intermediate signals between stations or between passing sidings, those run like normal ADS signals without the dispatcher having to do anything for those. What the dispatcher controls are the signals at the interlockings. So an interlocking, to give a few examples, would be at the end of a passing siding. Each end of the passing siding would be a separate interlocking or a control point. We call them control points on my railroad. The prototype would call them various things. So by setting up the signals at the CTC machine for the signals around an interlocking or a control point, that's how the dispatcher could authorize movement on the railroad. Here are a couple of pictures of prototype US&S CTC machines. You can see they all tend to be that same kind of bland olive gray color with the black, it's called the model board up on top. The levers are all laid out into columns, and if there's all the holes for all the lights and for all the lamps and for all the switches are all drilled out, and then ones that weren't needed were just filled in with plugs that you can see there. Not every US&S machine had the same functionality, but they're all very similar. There were occasions when railroads would want a different type capability, but for the most part, they looked very similar. Let's take a closer look at the CTC machine itself and how it's laid out. There's two fundamental parts to the CTC machine. There's the bottom part that has the levers and the code buttons, and then the top part that's called the model board. So let's first look at the bottom section here. My machine happens to have 16 columns. Everything is aligned in a column. That has the upper row of levers are the switch levers. These control the turnouts, the mainline turnouts on the CS&P. It's a 2-position switch. It has a normal position, and the R stands for reverse or reverse position when you're taking a siding. The signals have as a 3-position switch. There's a null position in the center when there's no route set up, and then there's an L position for a left-hand movement and an R position for a right-hand movement. So when you're using a CTC machine, the dispatcher's looking at the way the machine is oriented, and it's always a left or the right. Even though we know on the railroad there's east and west, or on my railroad it's north and south, the dispatcher thinks of left movements and right movements. So that's why his signals are L and R when you're depending on which direction you're setting up a route for. Below that is the code button. And it doesn't matter what you do to the levers above, nothing happens until you hit the code button. So if I go to turn this turnout and I put it in the reverse position, nothing moved, it's still in normal position. But once I hit the code button, that caused it to move to the reverse position. What you're hearing when I do that is actual recordings of all the relays that were inside these machines. So these machines were constructed before computers. They started constructing these in 1930, and basically they were full of relays. Somebody, I don't know who, has recorded these sounds in JMRI, so when you hit the button, it's actually displaying the sounds of a real machine through the speakers. So that's what you're hearing. The other on the machine is there are a few levers here for locking switches. So we have a couple of areas on the CS&P where turnouts need to be under local control because of local switching that is done there. So these levers here provide for the dispatcher to put those turnouts into local control where they're controlled by the local crews on the fascia and no longer under dispatcher control. So that's what this bottom set of 4 levers are for. So again, we have the switch levers, the signal levers, and then the code button. I'm going to put this one back to normal. The top part is called the model board. The model board is a simplified track schematic of the railroad. And it only shows trackage that the dispatcher cares about and controls. It is not to scale. It's just laid out with showing all the passing sidings and all the signals. So just to go through it quickly, you can see where each of I'll look over here, this is easier. This shows where each of the control blocks are. These white LEDs, this one's lit up because there's a train in this block, so they're occupancy LEDs, so the dispatcher knows which ones are occupied. There's another train in this block. The red LEDs, this is an important concept. This is an OS block. It goes back to the days of where station agents would write down a train passing by. So OS stands for on sheet or on station. But it's important because it allows a dispatcher to know that a train has entered an OS block and that he probably needs to do something, or it's left a station area, it's left a passing siding, or it's entered a passing siding. And these are not to scale. It's a long ways from this OS block to this OS block. This whole thing here is only about 10 feet on my model railroad. While this from here to here is probably 40 or 50 feet. So it's not to scale. It's just a matter of where the control points are that the dispatcher cares about. So these OS blocks, they also can be called control points. So on the CS&P, we call them control points or CPs. So those are all labeled. The turnout at this end of a passing siding is labeled as number 11, which corresponds to the switch directly below it is number 11 switch. So the dispatcher knows which turnout he's throwing. And then also the signals are on it. So he can see that the signals around this OS section are number 12. 12L stands for, that is for a left-hand movement heading in this direction towards the left or northbound on my model railroad. And 12 12R is right, 12RA and 12RB, just because there's two different tracks that could be going that way. So those signals correspond to the signal number here, number 12. So signals are always even, switches are always odd. There are some turnouts that are under the dispatcher control that there's no signaling associated with. So this switch heads over to an industrial park. These LEDs up here are directional LEDs, and you'll see when we run a train through that these LEDs will light up, and so the dispatcher, when he sees a train going on the single track between two OS points or control points, it lights up and tells him which direction that train is moving in. So this is the fundamental way that all US&S CTC machines are constructed, with the model board up top, and then the lever section down below, and then the code buttons. So in this scenario, we have the rail diesel car passenger train heading northbound towards Calgary here in Castlegar. It's at the station on the main line, and you can see it on the indicators being detected by the LCC system and displayed here on the model board. Over here in Nelson is Freight Extra 2014, which is heading southbound out of Nelson. So let's pretend this is the pre-Amtrak days, and the passenger train actually has priority over the freight. And so I'm going to set up a route in order to send the passenger train into Nelson, where the station is. So the first thing I'm going to do is throw the switch here in Nelson into the reverse position, hit the code button, which activates everything that I've changed in that column. Now I can see that the turnout at South Nelson has turned to the reverse position. Now, in order to give the passenger train authority to go, I need to set up a route. He's moving left. I know that's north, but it doesn't matter. It's everything on the CTC machine is oriented either a left movement or a right movement. So this is going to be a left movement. Now we're going to set up the route for the RDC to depart Castlegar and head to Nelson. So the way we do that is we start at the far end of the route of where we are, of where the next stop is for the train. So that's right here at signal number 12, which lines right up with CP 380 at the south end of Nelson. And so I'll make that into a left-hand movement. I'll hit the code button, and we can see that that is now set up for a left-hand movement. And then I'll go back to CP 399 here at the north end of Castlegar, and I'll set that up for a left-hand movement. And when I hit the code button, the signal for the RDC will turn green, and it can proceed. The engineer will see the green signal, and the train will begin to move northbound. It's just entered the OS block, which I heard the bell alerting me to that fact. And when it entered the OS block, it knocked down my route, because it's now passed through there, and it's gonna go all the way into Nelson. We can see the indicators here showing where it is. In addition, these are the directional indicators. So the machine is telling me as a dispatcher, so I know that this train is not only in this block, but I know it's moving to the left, or in the case on my railroad, which is northbound. So I can see both the direction and where that train currently is. Oh, the train has just entered the next block down, so it's past the halfway point, and it should be coming up onto into Nelson shortly. As soon as it enters that OS block, I will hear the OS bell, and I will see that block light up red. So now I can see that the train has cleared the turnout and it's arrived at the station. So at this point, I can now route the freight extra and give it, even though the track is cleared, I have not set up a movement yet for the freight extra to depart on Nelson. So the first thing I'm going to do is normalize the switch. I could have done this actually in setting both levers before hitting the go button, but it doesn't matter. And now I'm going to set this switch up for this signal up for a right hand movement. I can see now that he's received a green. And he is able to depart from Nelson. Once again, I can see he's heading towards the right or southbound on this railroad through the directional indicator. The northbound passenger, RDC, has finished picking up his passengers in Castlegar, and the engineer moves out of the station and pulls forward to the signal at North Castlegar. The signal in North Castlegar is red, indicating to stop. The dispatcher is not yet aligned a route, has not yet set up a route for the RDC. As a dispatcher is aligned a route for the RDC, it now gets a green signal and is able to proceed northbound towards Nelson. As the RDC approaches Nelson, it sees a yellow signal meaning approach, which means he's going to be routed on. He's been routed by the dispatcher onto the siding where the station is. Yellow indicating to proceed at a slow speed since he's taking that diverging route. See, the signal turns to red once the RDC has passed into the control point. Once the RDC is cleared and the dispatcher has aligned the route for Freight Extra 2014, the signal goes from red to green, indicating clear, and the freight train can proceed southbound towards Castlegar. As soon as the freight train hits the OS block, the signal drops to red, protecting his rear end. I'm lucky to have two friends who were willing to help me out accomplish building the CTC machine, who have a lot of expertise. Dave Martini did all the mechanical engineering design. He put together the CAD packages and outsourced the mechanicals to a job shop. And Ken Cameron did all the JMRI programming for the LCC needed for the system. And before we got started on the design of the system and let alone the build of it, we decided it would be a good idea to put together a small test system. So there's a picture of it there. I put together a quick panel just made out of hardboard, and put a few of the components on it. And our goals is that we wanted to see to make sure that all the hardware that I found online, that it was actually available, and that it wasn't just, as we sometimes call vaporware, where it's online, but if you go to order it, you find out that it's not available. And also we wanted to get kind of one of each component so that Dave could use that as part of his mechanical design and figure out how everything had to align and how the levers and switches, attach to the panel. And also, Ken had an idea that he had read where he felt maybe we could cut down the number of LCC I/O boards, input-output boards, by time sharing some of the inputs and some of the outputs. So we built this little test jig there, and wired it up and drove some LEDs and panels. We definitely learned some things. Two things in particular. One is that the I/O time sharing approach turned out to be more complicated than it was worth. It wasn't really going to save that many boards, and it was going to add a lot of complexity. So we decided to just use kind of the standard I/O boards and the way that we had used them when doing the signaling of the layout. We also learned that the rotary switches, something I thought was going to be very simple, was not all that simple. And it turns out that you can't buy a 2-position rotary switch that has the 2 positions that are the proper angle apart from the for the switch levers. So it turns out that we were able to find an offering online particular to CTC machines, and instead of just buying the rotary switches from some electrical supply company, we realized that it would be much easier to spend the extra money and buy the rotary switches from CTC components. So that was a big decision. So we're glad. It probably took about a month to build this, but it definitely turned out to be useful. As I mentioned, Dave did the mechanical design for the CTC machine. He developed the CAD package, and there's 4 components, mechanical components to the machine. The first is the enclosure itself. The second is an electronic shelf which sits behind the front panel, and the LCC modules are mounted on it. Then there is the front panel where the levers and the code buttons reside. And then on the top part is a model board. And that was a challenge. Now, the first thing about the model board is that we decided that, unlike the rest of the machine, that we would make that out of sheet steel. And we did that as a separate piece. And we did that for a couple of reasons. One is we wanted it to be steel so that a dispatcher could use magnets of trains and run those along the model board in order to help him keep track of which trains were where. The second reason is that we were a little bit concerned that the model board might get screwed up when we went to take it to a print shop, or when we went to put a vinyl sticky on it, however we were going to decided to actually put the track schematic on it. So we figured if it was a separate piece, then if we had to go back to the machine shop, I would just be paying to have that piece redone as opposed to the whole front panel. And it turned out that was a challenge, the model board. First of all, we had to be very careful of all the LED holes on it. I can't remember exactly how many LED holes were on it. There's, I think the number is about 45. And they all had to be aligned properly with respect to each other and with respect to the levers down below on the panel. And actually, we went through that so many times, and we still messed up a couple of the LEDs. But luckily, I'm probably the only one that really notices, because it's just the directional LEDs are a little bit off. But everything else turned out to look good. And then a big challenge, probably what took the longest to do on this machine, was to get that model board printed. I felt fortunate in that I was able to find a print shop that had a machine to do it, and a proprietor. It was just a little mom and pop shop who was willing to do it. He was definitely interested. When I took it to him, I heard stories about, family members and friends that had trains. So he seemed to be on board with that. But then it took many months, just due to some business and personal reasons that the proprietor had, but also I struggled to get it in a format he could use, that he could use for his machines. I did the design of the model board actually using CAD Rail, and then I had to convert it over to a PDF file, and that turned out to be a fairly big effort, but it turned out great in the end, and I was thrilled with what I saw when I saw the model board finished. And there's a little story there too, because it really didn't cost me that much, because the proprietor, he was a good guy, and he ended up basically saying, hey, I just want you to pay for my materials, what my actual costs were, and if you just give me a tour for myself and my daughter of your layout, we'll call it even. So he spent a couple hours over here with his daughter one day, and enjoyed showing them the layout. This is what the back of the panel looks like with all the wiring. On the bottom, you can see that electronics shelf that Dave designed. Sitting on top of that are 9 LCC I/O boards, daisy chained together with those blue Ethernet cables. I'll talk a little bit later about the LCC network. There's over 400 connections between those LCC boards and the LEDs and all the rotary switches. It's not particularly difficult to do all the wiring. It's 2 simple circuits which are just done over and over and over again. I would tend to do this a column at a time. The real challenge was trying to keep the wiring fairly neat, and then also documenting it correctly. So I needed to document, as I made connections, every connection into those LCC boards, so that Ken could then use that information to configure those boards properly on JMRI. So this took a few months of wiring. It's something I could do kind of in front of the television, although when I sat behind this, I couldn't see the TV, but I could hear it. And so I would just kind of, make it a goal to go down and try to get, 1 rotary switch wired up or 1 column wired. And then just did that every day for a couple of months. Now, we don't have time to go into depth on LCC or layout command control, but as a quick overview, LCC is a fairly new standard developed by the NMRA. I think it's about 5 or 6 years old now, and it was really developed for control of everything but the trains. So it doesn't replace your DCC network to control your trains, but instead it can be used for everything else you might want to have on your layout. On the CS&P, we use it to control the signals, for turnout control. The tortoise machines are hooked into it, for train detection, and actually for sound modules as well, and now for the CTC machine. So we had an existing 13-node network underneath the layout, and basically we've added another 9 nodes to that. LCC is well supported with JMRI, which is software which is available for free on the internet. All of our LCC hardware came from Railroad Circuits. You can see a picture of their signal board. The signal boards are nice in that they provide outputs to control LEDs, as well as I'll call it standard I/O for things like switches and buttons. And 8 of the 9 nodes in the CTC machine are the signal boards, because we needed to drive a lot of LEDs. But there's also what's called a tower board, which just is used for actually all the code buttons. As I mentioned previously, the wiring behind the panel really just consists of 2 simple circuits, one for LEDs and one for rotary switches and the code buttons. As far as the LEDs go, the Railroad Circuits signal board is set up to drive 4 signals, if you will, on a layout. But those signals, being that they're just LEDs, we could use those drivers for the LEDs on the CTC machine. And the railroad circuit's signal board is set up to handle 4 signals with 4 colors: red, yellow, green, and lunar. So it can drive 16 LEDs, broken out to 4 to a common, if you will. So that's how they got wired in, with the commons being run through a terminal strip, just to make it simpler, but there's other ways that could have been done. As far as the rotary switches and the code buttons go, the code buttons could be simpler. One end is tied into ground and one end is tied into one of the I/O pins on the LCC board. The rotary switches are similar. The common is tied into the ground, and then each position that is needed is tied into one of the I/O pins on the LCC board. The only thing of interest there is that we were able to cut back on the amount of wiring and the number of I/O drivers we needed on the boards by using a null position. So, for example, when either a signal switch or a switch lever is in its normal position, if you will, that doesn't require a wire. So the LCC system and JMRI basically assume that if it doesn't see a signal, that it's in its default position. So that didn't need to be wired in. Just want to touch very briefly on JMRI. I was fortunate on this project to have Ken Cameron, a local expert in our division. Ken implemented all the JMRI that was needed for the machine. And JMRI stands for Java Model Railroad Interface. It's software that you can download off the internet. It's available free to anyone. It's well supported. There's a large active user group. There's a lot of online resources you can find in terms of video clinics and how-to manuals and frequently asked questions. So it's a very robust, very powerful software package that's available to model railroaders for free. On this project, we used JMRI to implement the CTC interlocking rules. Ken had already implemented all those rules when we had a virtual CTC machine before we implemented the one in hardware, so he was able to reuse all that. And JMRI was also used to configure all the LCC support that we needed. Things like configuring the boards. You have to define where every I/O and LED line is, and defining events, etc. So JMRI is very robust, very powerful, and it's available for anybody to use. The components used on the CTC machine came from 3 primary suppliers. So as I've mentioned previously, all the LCC components and hardware came from Railroad Circuits. Logic Rail has an offering of a lot of components, but what I ended up using from Logic Rail was the LEDs and the bezels that go around the LEDs. Those bezels are plastic, but they look good, and their cost was significantly less than the metal parts from control train components. So control train components provided the majority of the hardware that you see on the panel. They provided the rotary switches, both 2 and 3 position. And as I mentioned before, you can't just use any old rotary switch, because if you just go and buy a rotary switch from an electrical supply shop, the positions won't be in the proper locations. So control train components modifies the rotary switches so that they're in the proper locations. They also provided the lever assembly, the lever plates, the code button, and the bell cutout switch. So they have a full range of hardware which are replicas of US&S hardware. As a matter of fact, Control Train Components will actually build. They are willing, and they provided me a quote, which I'll talk about in a minute, to do an entire panel for you, or you can just buy hardware from them. Rick's products, they make a number of CTC parts. They're plastic. They're the levers and the plates, but they are plastic. They're much lower cost. You do have to paint those parts. And I've seen pictures of people who have made CTC machines using the Rick's products, and they look good. But I just decided to, to use the higher quality Control Train Components. Oh, and Control Train Components, you find them online by ctcparts.com. And sometimes when you talk to folks, they will interchange Control Train Components with ctcparts.com. It's the same company. Well, I'm sure some of you are wondering, how much did it cost to build the CTC machine? So just a quick walk through that is we did initially estimate it. I can remember Dave Martini and I sitting down and kind of just working through what we thought all the metal might cost, and just looking at how much LCC hardware, etc. And we estimated it would cost somewhere between $3,000 and $4,000 to build it. In the course of getting quotes for all the piece parts from CTC Components, and they were very responsive, they did offer to quote the entire job for me. And when I say entire, I'm really saying the enclosure, the panel, all of the the model board, all the hardware on the outside of the machine. It would not have included any of the electronics or wiring inside the machine. And so CTC Components will build a complete panel. They quoted, it was right around $6,000, which in my mind is fair, given that each one is kind of a custom job and the amount of labor it would take. They would have had to have, done all the print screening, silk screening for the model board, etc. But it was around $6,000. I viewed it, if I went that path, and I did consider it, that it would have been closer to $7,000, given once I added in all the LCC hardware and all the various miscellaneous electrical hardware inside of the machine. But the final cost was right around $3,000. Is what I spent on material. So it's $3,000 material plus a few hundred hours of my labor and Dave Martini's labor and Ken Cameron's labor. So I feel that $3,000 was well spent, given the added interest and the fun of operating the machine, and having something that is somewhat unique on my model railroad. So it's, in my mind, it was definitely worth it in the end, given all the benefits it's provided.